We're now going to hear from Dr. Jay Gambetta, IBM Fellow and Vice President of Quantum Computing at IBM Quantum, on plotting a no-nonsense path to quantum advantage. Dr. Jay Gambetta.
I'm very happy to be here. I'm going to talk about a few things that we've actually never talked about before, so I hope you'll enjoy it. I'm going to do my best to get it in 15 minutes, so expect a lot of information coming fast. So from my perspective, we've been commercializing quantum computing ever since we put the quantum computer on the cloud in 2016. Today, we have over 20 systems that are operational. Many of them are free. If you haven't gone and used a quantum computer, go right now and start programming. Some of them you can pay $1.60 a second, and my slide, sorry, it's up there, $1.60 a second and run them, and there's over 410,000 users running like 3.5 billion circuits. The other area, and I'm not going to talk at all about this today, is the business side of and working with our IBM Quantum Network. We have over 180 members that are working on applications, software stacks, collaborating with us on how we make this simpler and simpler. If you want to know more about this, we actually have a partner in the audience that can give you more information. I'm also from day one, we cared about workforce, diversity, how we get it into classes, and we focused on bringing this and getting this as much as we can and get that talent trained. And Liz will talk about this in a panel tomorrow. And as a scientist, well, former scientist, I don't know what I am anymore, I love to see that papers are getting published. So what am I going to talk about today? I actually think we have confused the world. I think people have used this word NISC. I have always disliked it, and it seems to be let's just put something together and hope for the best. I've seen fault tolerance, and I honestly think people don't know what it means, and somehow it's equated to let's build a logical qubit. And obviously, quantum-inspired is another way. So what I'm going to talk about today is where we've always had a third way, and we've been pushing a third way. And I'm not going to say I don't believe in error correction. I'll tell you and talk to you about that, but I'll start to present and make viable the way that we're going forward. But just to go a step back, if you want to do a quantum application, the only thing that matters is the complexity of the circuit that you're running cannot be simulated classically. So everything comes down to these quantum circuits that get run and how you run them on your hardware and them not having an easy ability to simulate them. And if we go to high-performance computing, the critical question is, what is the time to run the solution of a problem of interest? So instead, I want to propose that we really should be asking the question, what is the time to run a noise-free estimator of a quantum circuit? And what I mean there is key noise-free estimator. So what I'm saying for the no-nonsense path is there's two parts. One, how do you map these applications that you've heard many people talk about to quantum circuits? This is a really hard question, and there's not a chance I can touch on it in this talk, and we put a lot of effort of this in our network. The second is, how do I run quantum circuits and get estimates on hardware faster than I would do on classical? So to go on them, the first one has to be a partnership. Very much, it is not going to be answered by IBM alone. It's not going to be answered by anyone alone. It has really got to be a partnership to work out how to do that one. The second is, can we come up with a way that we can develop a path to run these circuits faster on quantum circuits? And rather than be bound by fault tolerance, which really is long-term and where we need to go, why that is so exciting is the runtime for that is linear. What we're actually finding as we develop noise error mitigation is that the runtime can be exponential. And you can think of it as, can I come up with a way where I can run many circuits and run them, combine them together, process them, and give a formula for how long it takes to run them? And there's some simple parameters in there. Obviously, delta is the speed. In terms of a metric I put out, you can relate it to clocks, how fast you're running circuit layers. Gamma is a parameter. I'm not going to have time really to go on it, but you can think of when you finally have fault-tolerant error correction working, it goes to 1. N is the number of qubits. And so by taking this formula and understanding, and I'll show where we've done some demonstrations on it, you can think of the way that I advance and push this runtime is either by pushing the speed, quality, or scale. And I keep always pushing those three things. How do we keep pushing the speed, how do we push the quality, and how we push the scale? So my view is the path to making quantum circuits run faster on quantum hardware is increasing the speed, quality, and scale. So scale. Scale is the number of connected qubits. We put out last year the Eagle, which is 127 qubits. The key innovation here is all the qubits are on one layer, and we can separate the I/O and resonator layers, so this gives us a path forward to scaling to 400 and 1,000 qubits on a single chip. And I'll talk more about how we're going to go beyond that and scale later. Quality. Quality is essentially how good is the circuits that you run doing the bare quantum mechanics. So fundamentally, you've got to push coherence. We are always working on coherence, and here I'm showing our latest commercial devices, Falcon R5, R8, and some of our test devices that are reliably getting over a millisecond, pushing into the 3 milliseconds of coherence. Down the bottom, I show where we are on our exploratory devices. We now, on the Falcon R10, which is a new chip that has got a different architecture of a gate, we're reliably getting 3 nines fidelity, and pushing that even further and further into, I believe, by the end of the year, 4 nines. And so putting all this together, our goal is to keep plotting this as the quantum volume. So if I think of quality, I think at the bare is coherence and gate errors. I'll come back and give a bit more of that in 8 minutes. So speed. Speed. You need faster ways to read it out. You need faster ways to process circuits. You need faster electronics. All these things go into pushing what it means by speed. And the Qiskit runtime is exactly that. It's a containerized environment that allows you to program circuits at speed. And so if we take this into an equation and we have an estimation, you can do your best classical simulator with whatever type of method, and it's going to be, I think the leading classical method to date is by Sergey Bravi and David Gossett. It has about a 1.262 to the power of n related to the orchestra, how you scale it and map it out. And if you calculate the gamma that you need to beat them, you get out that for 100 qubits, you need to get this gamma parameter of less than 1.003. So where are we today? On the Brooklyn, which is a 65 generation 1 qubit, we measured 1.075. On Ithaca, which is a 65 generation 2 Hummingbird processor, we measured 1.041. On that new architecture, that internal device that I talked about, that we're pushing up into the 3 nines, we're measuring 1.008. And so what you can see here, and even shown in this plot, is the estimations of a quantum circuit without running this noise-free error mitigation technique. In the blue, it exponentially decays. The weight 50 observables are just basically decayed down to no signal. And then you ask, well, let's do it for everything else. And it goes to 1, exactly giving you a noise-free estimate of what that quantum circuit would do. If you take these noise values today and you keep scaling it up, because I gave that formula before as an exponential, it will be too long to run. It won't be until we get down below 1.001 that you start to be able to get noise-free estimations using hardware. And my view is by getting to it, you can do a simple calculation, and 4 nines fidelity puts you well beyond that. And you'll be able to run 100 qubit circuits, get noise-free estimations of them, and be able to start to estimate what they do. And even more exciting, the team is starting to show how you can combine error correction and error mitigation. So you can actually mitigate certain things, error correct others, and what this fundamentally does is it starts to show, and my conjecture is we'll continually to show a continuous path of running these circuits with a faster runtime than we can do classically, and our goal is to get them implemented and get this as a tool that can be able to be used this. All right, change of gear. The next thing is, everything you can think about today in the first part was about how you actually run those circuits of a certain size and run them on hardware, get a noise-free estimate so you can actually predict something of value in the future. What's also coming really, really exciting is combining classical and quantum. And I already obviously have to combine classical to make the circuits run faster and do the mitigation techniques, but this is a different type of classical. This is a classical where you allow the classical, I like to say, to be elastic, to increase. And so if you start to think and you say, you know, in HPC or larger problems, the key was how do I take a big problem, a big circuit, and bring it down into smaller circuits? Very simple statement. And what we are actually finding, and it's very exciting, is we're finding there are techniques that are emerging continuously of how I break a big problem into smaller problems, and then I can knit them back together using classical resources to simulate the bigger problem. So on the left, I talk about embedding. So you imagine you have a classical solution driving a quantum active space. In the middle, I talk about circuit forging, which is essentially you take some linear algebra problem and you calculate an eigenvalue decomposition, and then you solve smaller problems and then sum them back together. And on the right, I'm talking about circuit cutting, which is another technique of joining them together. So this is sort of saying, well, I take classical and I mix it with quantum and I can do a bigger problem. But there's more. If you want to actually even cut a bigger problem, take a bigger circuit and cut it into a smaller circuit, and this is recent theoretical results, if I give you the ability to classically communicate in real time between independent processes, the classical overhead of that cutting you can actually show as a smaller number. You can show that if I was to cut a swap, which would have a coefficient, a classical overhead of 7 times the number of swaps I cut, goes down to 4. If I cut a C0, which would have 3, it goes down to 2. So this says, let's build an architecture where I can run quantum circuits, I can error mitigate them, and eventually error correct them, and let's build an architecture where I can classically communicate in real time between them. So my view is by the combination of elastic compute and classical computing, we will make this quantum advantage happen earlier. I'm not going to comment on how we map it to the circuits, but I believe by 2023 we'll be running circuits faster on quantum hardware than we can simulate them classically. So what is our roadmap to do this? So first, in 2023, if you haven't seen this, I'd recommend to go check it out. We made a video. We're making classically parallelized of quantum processes. The reason why this obviously, now I hope people can understand, this allows us to do that circuit cutting technique and be able to run many of these classical processes together. So here is the 133 qubit chip. It's a Heron. It's built from that architecture that had 3 nines. And so we imagine an architecture where many of them are connected classically. Next, 1,000 is about the limit I'm going to fit on a single chip. So how I go beyond a single chip is multiple chips. So the cross bill, which is shown in this animation, is about how do I bring and start stacking those chips together to allow me to scale up. And our goal is in 2024 to demonstrate multi-chip single processors. At the same time, we want to demonstrate, and that's called cross-bill, Flamingo. And Flamingo is this idea of how do I start to bring medium-range quantum communication between my chips. So if I got classical communication, and now I give quantum communication, in a longer talk I could tell you about the different types of applications and circuits that map to this, but this gives you an architecture where we can start to actually connect these chips together. So the 3, Heron, we're going to show classical communication between quantum processors. Crossbill, we're going to show how we continue to scale up with multiple chips. And then Flamingo, we're going to show how we go and get quantum communication to that. Putting them all together, and I'm sorry I'm going so fast in 15 minutes, 2025, our goal is to bring, and I'm bringing back to my Australian heritage, the Kookaburra chip, which is going to combine both of these technologies. And by putting this together, we actually think we will get 4,158 qubits. So I think all of this, when you go together, and you can imagine goes further, and you can keep combining multiple of these together and going to larger and larger of these. So you see, once I can start stacking and putting these together and start this technology, I can scale out to any numbers I want to get to. And here's an example of about 50,000 qubits. And this forms what we call quantum-centric supercomputing. And like many have talked about, I strongly think this is the next step in what computing is going to be. And in the last 40 seconds, I will finish by saying, I do strongly believe that the future is classical and quantum, but when you've got to really think about what you mean by classical. And there's various different ways. There's classical to make sure you can make a runtime of quantum circuits faster, and there's classical to allow you to use classical resources to extend what you can do. And if you haven't seen it, we make our roadmap public. We're committed to delivering on this, and this roadmap, we just updated it a couple of weeks ago, and so you see it's charted out to 2025, and for those all that want to know in 2026, you're going to have to wait for next year. And on that, thank you.